Hello, this is your instructor for Economics 170, a class in Statistics for Business and Economics. Almost all business students, whether they're accounting majors, finance majors, business management majors, almost all business students have to take at least one and possibly two classes in statistics during their college career. I assume that you haven't had statistics before, although some of the material that's early in the course should be somewhat familiar to you. So let's do a little introduction to the nature of statistics. First, what is statistics? There's various ways to define statistics. One way is to define it as a branch of mathematics that deals with the collection, presentation, analysis, and interpretation of data. Perhaps a simpler way is to just call it the science of numbers. The basic nature of statistics is we start with the idea of a population. Population refers to all data of interest to the researcher. We tend to think of population as referring to people, but in statistics, population refers to a body of data. It might refer to people, it might not. Similar to the idea of population meaning people, if you are able to take a complete enumeration of all data in the population, we call that a census. Most of the time, however, we will not be able to do this, because if the population is large, it's going to be very time-consuming and costly to gather all of that data. Therefore, we generally have to rely on a sample of data. A sample is defined simply as a subset of the population. It's just a little chart here kind of illustrating the relationship between population and sample. We generally have a larger population, but we're going to have to rely on some subset of that population, which we'll call a sample. When we say we're interested in the population, actually we're interested in specific characteristics of the population, which we will call parameters. A parameter could be the mean of the population, or some proportion measure of the population, or some measure of variability. A statistic, by definition, is actually a characteristic of a sample. So if I take a sample and calculate the sample mean or sample proportion or variance, I have a statistic. You'll notice that basically a statistic is to a sample what a parameter is to a population. As we said a minute ago, the population is generally unknown, meaning that you cannot gather all of that data, and therefore under most circumstances you won't know the exact values of the parameters of the population. One of the most important uses of statistics is to estimate and test hypotheses about those population parameters. I usually like to think of statistics as broadly broken down into three areas. We have methods of gathering data, which by and large means methods of taking samples. This is not going to be a topic that we spend too much time on in this course. Generally, in a beginning course in statistics, you assume the data has been gathered properly. But we will, in a future module, take a little look at ways of gathering data and some different methods. The second and third branches of statistics we'll spend more time on. Descriptive statistics, number 2 there. We will spend a couple of modules on descriptive statistics. And ultimately, we want to get to number 3, statistical inference. Descriptive statistics refers to tables, graphs, and also numerical methods that can be used to put data into a more organized fashion, to help summarize it, etc. And as I said, we will spend a couple of modules on descriptive statistics. Ultimately, what we want to get to in statistics is the idea of statistical inference. Gets the name statistical inference from the idea, what can we infer about this larger population and the parameters of a population when we have only a sample of data and the statistics from that sample? As we'll see, the major branches of statistical inference are, first of all, estimation. Can we make estimates of things from the population? And secondly, hypothesis testing. Could we test hypotheses about the parameters of the population? Statistics is used all over the place these days, especially in business. Again, as I said earlier, some of you are accounting majors, business majors, finance majors. All of these different areas use a lot of statistical analysis these days. Accountants often go into a firm with thousands of accounts. They don't have the time or resources to look at all of the accounts, so they take a sample of accounts. Manufacturing firms, especially ones that produce parts, especially in the area of quality control, often have to take samples in order to test for defective parts, because it's usually impossible to test every item of the population. Economists use a lot of statistical analysis, especially in making forecasts of future economic trends, economic growth, etc. Other areas of business also use a lot of statistics these days. One of the things that has really changed the nature of statistics for business in the past few decades has been the advent of microcomputers. 50 or 60 years ago, only the largest firms could do statistical analysis or had the money and resources to take large numbers of samples. But today, with microcomputers, it's become much easier for small to mid-sized firms to engage in statistical analysis. When we gather data, there are 4 different scales of measurement that can be utilized: nominal, ordinal, interval, and ratio. Depending on what scale of measurement you have, it will call for different types of statistical analysis. The nominal scale is sort of the lowest scale in a sense. Outcomes of the variable are just labels or names. We could put a numeric value on those names, but it's still just a name. And there's no way of ranking the data. A simple little example is gender, male and female. If we want, we could arbitrarily assign a number to each category. Let's say the males are number 1 and the females number 2, but those numbers do not have the usual properties of numbers, meaning 2 is not necessarily greater than 1. It's simply a label that's being used. The ordinal scale has all the properties of nominal, but in addition, the order or rank of the data has some meaning to it. If a firm sells shirts in small, medium, and large, it's understood that larger shirts are in some way bigger than medium and small. So the ranking there has some meaning to it. In your college class, if students are classed as either freshmen, sophomores, juniors, and seniors, it's understood that seniors have more credit hours than juniors, more credit hours than sophomores, and so on. The interval scale of measurement has all the properties of ordinal, but in addition, the difference between observations has meaning, but the ratio does not. The classic example here is temperature. If we say it's 60 degrees, it's understood that that's hotter than 30 degrees, but can we say that it's twice as hot? No, that ratio really doesn't have meaning. The gap between 60 and 30 has some meaning. 60 degrees is warmer than 30, but the ratio does not have any meaning. Finally, we get to the ratio scale of measurement, which has all the properties of interval data, but also now the ratio between two values has meaning. Variables like age, income, sales of a company all utilize the ratio scale. If one person in your classroom is 40 years old and somebody else is 20, it's understood that the 40-year-old is twice the age of the 20-year-old. If one person has an income of $80,000 a year and somebody else has an income of $40,000 a year, it's understood that $80,000 is double the $40,000 income. So the ratio has meaning in this case. Another way to classify data is to classify it as either categorical data or quantitative. And a second way to go about it is to look at cross-sectional and time series data. Let's start with categorical and quantitative. Categorical data, which is also sometimes called qualitative data, means that the outcomes of the variable are simply names or labels that identify one element from another. Whereas with quantitative data, notice it has the word quantity just about in it. Quantitative data always indicates how much of something. As we'll see in a minute, quantitative data is always numeric. Categorical data uses either the nominal or ordinal scale of measurement, whereas quantitative data uses either the interval or ratio scale of measurement. As I said a second ago, quantitative data are always numeric. Again, some of the examples we gave earlier, age, income, sales of a company. Immediately a number comes to mind when you hear of these things. Categorical data can be numeric if we want them to be, or they can be non-numeric. As we talked about before, sex, male or female, is a categorical variable. If I wanted to arbitrarily put a numbering system on it, I could, but I don't have to. Occupation, electrician, carpenter, accountant, manager. Again, that's just categorical data. Each outcome is just a category or a class that separates it from the others. We could arbitrarily put numbers on those different classes, but they don't have all the usual properties of numbering systems. What region of the country you come from, north, south, east, west, would also be an example of categorical data. Ordinary arithmetic operations are meaningful only with quantitative data. You have to have a numeric variable that's quantitative in order to do regular arithmetic operations. The other way of defining data or classifying data is to classify it as either cross-sectional or time series. With the cross-sectional data, all the data comes from roughly the same point in time. If a company took a sample of firms to find the beginning wages of workers on January 1st of this year, each outcome in the sample was taken at the same moment in time, and so that's a cross-sectional type of data. With time series data, every element in the sample comes from a different time period. For the company that you work for, if you gathered data on monthly sales for each month in the past 10 years, then obviously each observation comes at a different point in time. Once again, one of the reasons why we make these distinctions is there's different types of statistical analysis for cross-sectional data as opposed to time series data. Just like there is different types of statistical analysis for categorical variables versus quantitative variables. Where does data come from? Well, there's lots of data sources. In fact, today there's probably more data available than in most of our history. Government agencies gather a lot of data. The Census Bureau, the Labor Department, does a lot of data collection. Firms themselves these days more often are keeping their own databases, especially because of the ability of computers to gather data easily. You'll even find a lot of data available on the internet these days. And there's a lot of industrial organizations and things of that nature that also gather data. Let's get some basic notation and math symbolism out of the way. We've talked about the difference between a population versus a sample. We let capital N represent the number of elements in the population, and little n represents the number of elements in a sample. The symbol X will be our basic variable symbol throughout the course. Some books might use Y or Z, but we tend to use X here in this class. Most of you are probably already familiar with summation notation from other classes you've had. Summation notation is just a shorthand way of writing a sum. There will be many times in statistics when we want to add up a series of numbers. For example, here, let's say I want to add x1 plus x2 all the way out to xn. Instead of me writing this out over and over and over again, we can simply write the sum of the xi's starting from I equal 1 to I equal n. This symbol here is the capital Greek sigma, which we refer to as the summation sign. The I equal 1 and I equal n is called the index of summation. Tells you where to start the sum and where to end the sum. So this basically says start with I equal 1, and we'll have x1, go to the next integer, add in x2, and continue until you get to the nth value. In almost all cases in this course, we're always going to be adding up all of the data, all n observations, in which case I don't have to bother putting the index of summation on here. I can just write summation x, and it's understood that you're going to add up all values of x. A couple of properties of summation, and for the most part, you're not going to have to worry about this because we don't do a lot of proving of things in this course. We leave that up to the mathematicians in the more advanced statistics classes. But there may be one or two places where we have use of a couple of properties of summation. If c is a constant, and we said sum the constant from I equal 1 to I equal n, that's just going to be equal to n times the constant. Basically, summing a constant from I equal 1 to I equal n means you're adding the same number up n times, and if you add the same number up n times, that's just n times that value. A second property, the sum of a constant times a variable x. The basic property here is that you can pull the constant out in front of the summation sign. This is equal to c times the sum of the x's. That actually just comes straight from factoring. Here you would have cx1 plus cx2 plus cx3, and you can factor out that c. And the last one that we'll look at, the sum of a sum, basically, if we had two variables, x and y, and we wanted to find the sum of a new variable, xi plus yi, basically it's going to equal the sum of the parts. It's equal to the sum of the x's plus the sum of the y's. Again, for the most part, you don't have to worry about these properties of summation because there's very few places where we will utilize them. We're not going to get too mathematical and so on. One last little topic that we're going to cover in this introduction has to do with ethics in statistics. Many business students now have to take classes in ethics. A lot of business programs have added ethics to their degrees. Ethics, of course, deals with your sense of right and wrong. And there are things that we can do wrong in statistics. As I say there, you might have heard the expression that there are lies, damned lies, and then there are statistics. Well, statistics don't lie, but sometimes people lie, or sometimes people utilize statistics in a way that might give the wrong impression. The American Statistical Association has established guidelines for responsible statistical work, and if you like, you can go to this website and read a little bit about that. An example of unethical behavior might be in the example right there, running multiple tests until a desired result is obtained. Let me explain what I mean by that. How many times have you watched a TV commercial and you've seen something of the following nature? In a recent study, 70% of the people preferred our product over our competitors. There's a couple things they don't tell you here. First, they don't tell you how large of a sample was involved in coming up with this 70% figure. And they also don't tell you, did they have to run the test over and over and over again? For example, suppose we just take a sample of 10 consumers and we have them compare two products. Let's say in our first sample, it's split evenly down the middle. 5 people prefer our product and 5 people prefer our competitors. That doesn't sound very good for our purposes. We throw that sample away. That's not the one we want to publish. We take another sample of 10 people and test them on these two products. And we keep doing it until eventually maybe we get one sample where 7 out of 10 people prefer our product. Well, suddenly that gives us the one that we want to advertise. We say in a recent study, 70% of the people chose our product over our competitors. We just don't tell people that we ran the test multiple times and that we only chose 10 people. That would generally be considered to be unethical and would not be looked upon very favorably in the statistical world these days. From time to time in the course, we will mention some things that could be possibly unethical behavior. We're going to stop there for our introduction to statistics.